Okay, I want you to stop for a second, right where you are, and listen. Can you feel it? That silent, kind of intimate rush? That current, that just pulls you from the moment that just happened into the next one? That's time. We feel it, like deep down. We track it. Our whole lives are built around its flow.
It really is the most basic feeling we share, isn't it? And forever, people have tried to capture that feeling. Think about myths, like the dancing Shiva in Hinduism, his cosmic dance, keeping the universe flowing. It just feels like this absolute river carrying us along.
And yet, here's the kicker. Modern physics basically forces us to confront this massive contradiction. It's like finding out the Earth isn't flat, or that the sun doesn't circle as the structure of time. It's really not what it seems. That smooth universal river, it turns out it's probably more like an approximation, an illusion maybe, born from how we look at things, what time actually is. Well, that's maybe the biggest mystery left, tied up with consciousness, the Big Bang, everything.
Yeah, and that's exactly what we want to do in this deep dive. We want to take that idea of time you have, like a perfect little snowflake, hold it up, and then just watch it melt away as science looks closer. We're going to see how it crumbles piece by piece. Then we'll look at the weird sort of timeless picture physics is left with. And finally, this is crucial, we'll try to figure out where the time we do experience actually comes from. Because it's not one simple thing. It's layers, structures, approximations. Depends on who's looking, basically.
Okay, so let's dive into that crumbling. The first big piece to go, unity. The idea that time ticks the same everywhere for everyone. That was always the bedrock.
It was the intuition, definitely. Yeah. But now it's just a measurable fact that it's wrong. We have atomic clocks now, incredibly precise things. And they show, undeniably, that time doesn't pass uniformly. It runs faster, say, on a mountaintop compared to sea level, measurably faster.
Whoa, hang on. Let's make sure we get this. We're not talking about weird stuff near black holes yet. You're saying, like, right here on Earth, a clock on my desk runs faster than one on the floor.
Exactly. The difference is tiny, minuscule, but it's real and measurable. Even between levels just a few centimeters apart, if your clock is good enough. Think about it with that classic analogy. Two friends. One lives high in the mountains, the other down by the coast. When they meet up years later...
The one on the plains will be slightly younger.
Slightly younger, yes. They will have experienced less time. Fewer clock ticks, fewer thoughts processed, less biological aging. Down lower, closer to the mass of the Earth, there's just less time available. Period.
And Einstein figured this out, like, 100 years ago, before we could even test it.
He did. General relativity. His insight was that massive objects, like our planet, don't just sit in space and time. They actually warp it. They change the geometry around them. Think of putting a heavy ball on a stretched rubber sheet. It creates a dip. Earth does that to space-time. And part of that dip, that warping, is that time itself slows down closer to the mass.
So the planes are deeper in that time. Well, so time runs slower there.
Precisely. And that changes everything we thought we knew about gravity. Why do things fall? Not some mysterious pull. It's because things naturally tend to move towards where time flows more slowly. It's like rolling downhill on that rubber sheet.
Yeah.
When you stand up, your feet are literally in a zone of slower time than your head. That's why you stick to the ground. Mm-hmm. You're constantly falling towards the slower time at your feet.
Okay, mind blown already. So if time stretches and shrinks depending on gravity, then the whole idea of one single universal time just falls apart. There's no master clock for the universe.
It completely collapses. Physicists call the time measured by a specific clock its proper time. And since every clock moving differently or located differently measures a different proper time, asking which one is the real time is, well, it's meaningless. It's like asking if a dollar or a pound sterling has the truer value. They're relative. Their value depends on the exchange rate, on the context. So we don't have one time. We have countless proper times, billions upon billions, a unique one for every possible path through space-time. Time has lost its unity. The world isn't a lockstep march. It's a network of events influencing each other at different rates.
Wow. Okay. That's a huge loss. But we're just getting started, you said. The next thing to go is direction. The arrow of time. That feels even more fundamental.
It does, doesn't it? That feeling of flow, from past to future, memories behind us, possibilities ahead, regret, anticipation.
Yeah.
That's core to being human. The broken glass never reassembles itself. Why? Why only one direction?
Yeah, why is the past so different from the future?
And here's the deep, deep puzzle. Look at the basic laws of physics. Newton's laws, Maxwell's electromagnetism, Einstein's relativity, even quantum mechanics. They are remarkably time-symmetric. What that means is, if a process is physically possible according to these laws, the reverse process is also possible. A movie of billiard balls colliding makes sense, run forwards or backwards according to the basic physics. The deep grammar of the universe doesn't seem to care about past versus future.
Wait, hold on. That can't be right. If the laws don't care, why does everything we see care? Why do eggs break and not unbreak? Why do we remember yesterday but not tomorrow?
The only place the difference reliably appears in physics is where there's heat. Think about it. Any process where you clearly see the arrow of time involves heat or energy dissipation in some way. A bouncing ball eventually stops its energy, turns into heat through friction and air resistance. Our brains process thoughts, creating memories that neural activity generates heat. Heat seems to be the key.
Heat. Okay, how did physicists connect heat and time's arrow?
It actually started with steam engines back in the early 19th century. A French engineer, Sadi Carnot, was thinking about efficiency. He realized that engines work because heat naturally falls from a hot source to a cold sink, like water falling downhill.
Ah, okay, so heat flow has a natural direction.
Exactly. And then Rudolf Clausius formalized this. He stated what we now call the second law of thermodynamics. Heat won't spontaneously flow from a cold thing to a hot thing unless something else changes. It just doesn't happen. And to quantify this, he invented a concept called entropy, usually written as S. Entropy is a measurable quantity, and the core idea is that in any isolated process, the total entropy can only increase or stay the same. It never goes down. The equation is delta S, enter little town. Look across all of fundamental physics. This is the only basic law that explicitly talks about the direction of time, about things only happening one way.
Entropy, the disorder thing, right. So time flows because things naturally get messier.
That's the popular idea, largely thanks to Ludwig Boltzmann, a brilliant, somewhat tragic figure in the late 19th century. And ironically, his grandfather was a clockmaker. Boltzmann realized heat isn't some weird fluid, it's just the random jiggling and bumping of atoms and molecules. Hot stuff has fast jiggling molecules. Cold stuff has slower ones.
Okay, that makes sense.
Now think about shuffling a deck of cards. You start with it ordered aces, kings, queens, all together. It's a very specific ordered state. You shuffle it once or twice, it gets mixed up. Keep shuffling. It gets more and more random, more disordered. It's overwhelmingly more probable that shuffling leads to a disordered state than back to the perfectly ordered state. Boltzmann said that's what happens with heat and molecules. Things naturally move from order to disorder because there are just vastly more ways to be disordered. The growth of entropy is this constant natural shuffling towards messiness.
So the arrow of time isn't in the fundamental laws of motion, but in the statistics, in the probability of things getting scrambled?
Precisely. It's a statistical effect.
Yeah.
But then Boltzmann took it one step further, and this is where it gets really mind-bending. He started thinking about why we perceive order and disorder in the first place. He argued that disorder, or high entropy, is related to how much detail we ignore. Think about watching a movie. If it's super high definition, 8K, every single frame looks unique, detailed. But if you watch a blurry, low-res version...
Lots of frames might look basically the same. You lose the detail.
Exactly, you've blurred your vision. Boltzmann suggested entropy exists because we perceive the world in a blurred, coarse-grained way. We don't track every single molecule. We only notice macroscopic properties like temperature and pressure. Entropy, mathematically, is a measure of how many different microscopic arrangements look identical to our blurred macroscopic view. It counts the hidden information we're ignoring.
Whoa, so you're saying the arrow of time, the difference between past and future, only exists because we have a fuzzy view of reality, because we're ignorant of the details.
That's the staggering conclusion, yes. If we could somehow perceive the exact quantum state of every particle in the universe, if we had perfect information, Boltzmann argued the difference between past and future would dissolve. Every state would be unique, and the statistical trend towards disorder wouldn't apply in the same way. The arrow of time seems to be a consequence of our limited perspective, a reflection of the fact that the universe started in a state that looks very ordered to us, given our blurred way of interacting with it. Time has lost its fundamental direction. It's become an emergent property of ignorance and statistics.
Okay, this is a lot. Unity gone, direction gone. What about the present, the now? You mentioned Einstein tackled this even before gravity.
Yes, 10 years before general relativity, his theory of special relativity dealt with motion and time. And one of its key predictions, now verified countless times, is that speed slows down time. The faster you move, the slower your clock ticks relative to a stationary observer. Think of clocks on airplanes or satellites. They genuinely run slightly slower than clocks on the ground due to their velocity.
Right, the twin paradox kind of thing. One twin travels fast, comes back younger.
That's the one. But this has devastating implications for our idea of a universal now. Let's go back to your sister on Proxima b, 4 light years away. When you look through a telescope, you see her as she was 4 years ago because light takes 4 years to get here. But the killer question is, what is she doing right now? Special relativity reveals that there's no single objective answer to that question. The concept of now isn't universal.
Why not? Can't we just account for the light travel time, subtract 4 years?
You can define a now for you based on your motion and location, but someone moving relative to you at a high speed would calculate a different now on Proxima b. There's no privileged observer whose now is the real one. Asking what's happening now on Proxima b is fundamentally a meaningless question in physics. Like asking, I don't know, what's north of the North Pole? The concept breaks down.
So now is just local, a bubble around me.
Pretty much. The size of that bubble depends on how precisely you need to define now. If you only care about time down to, say, 1/10 of a second, then now can pretty much cover the whole Earth, because light travel times across Earth are much smaller than that. But if you need nanosecond precision, your now shrinks to just a few meters around you. Outside that tiny bubble, simultaneity is relative.
So what's left? If there's no universal now, how does physics describe the temporal structure?
It uses what's called a partial order, structured by light cones. Imagine an event like snapping your fingers right now. There's a cone extending into the future containing all the events you could possibly influence, limited by light speed. That's your future light cone. And there's a cone extending into the past containing all the events that could possibly have influenced you, your past light cone.
Okay, I can picture that. Past influences me, I influence the future.
Right. But here's the crucial part. For a distant event, like something happening on Proxima b, there's a whole region of spacetime that's outside both your past cone and your future cone. It's neither in your past nor your future. This region is sometimes called the elsewhere, or the expanded present. For Proxima b, this interval is 8 years long. For 8 whole years, events happening there are in a kind of temporal limbo relative to you, neither past nor future.
8 years of neither past nor future. That's deeply weird.
It is. And general relativity adds another twist. Massive objects warp these light cones. Near a black hole, the cones tilt so much that once you cross the event horizon, the future cone points entirely inward, towards the singularity. The future literally is the center. There's no escaping because moving forward in time means moving towards the singularity.
Wow, so the present isn't just relative, it's fundamentally non-existent on a cosmic scale. Another pillar down.
And that leads us to the next casualty. Independence. The idea that time exists as a separate, fixed background, independent of what happens in it. Where did that idea even come from, given how flexible time seems to be?
Well, I guess Newton, right? Didn't he need an absolute time for his laws to work everywhere?
Exactly. Before Newton, you had figures like Aristotle who thought time was just the measure of change. If nothing changes, time doesn't pass. A relational view. But Newton, for his physics of motion and gravity to work mathematically, proposed this concept of absolute, true, and mathematical time that flows equably without relation to anything external. It's like a universal stage, completely unaffected by the actors on it. Clocks just try to measure this absolute flow.
And that became our default way of thinking, didn't it? It feels intuitive the clock ticks, regardless of whether the Earth spins or not.
It does feel intuitive. But Einstein, again with general relativity, showed Newton was only half right. He agreed space and time are real physical things, not just ideas. But they aren't absolute or independent. Space-time is the gravitational field. It's not a static background, it's a dynamic entity, like the electromagnetic field. It can bend, stretch, ripple as gravitational waves, and interact with matter and energy.
So time isn't the stage, it's part of the play. It's an active participant.
Precisely. It's a component of this dynamic gravitational field. When you see those diagrams of curved space-time, it's not just space that's curved. Time is stretched or compressed, too. The field dictates the rate at which physical processes unfold, so time has lost its independence. It's woven into the fabric of the cosmos, influencing and being influenced by everything else.
Okay, so we've lost unity, direction, the present, independence. What's left to crumble? You mentioned continuity.
Right, the final piece, at least according to our current best theories, trying to combine gravity and quantum mechanics, the field of quantum gravity. When you bring quantum effects into the picture, even the smooth, continuous nature of space-time described by Einstein seems to break down.
Quantum means discrete. chunky.
Exactly. Quantum mechanics tells us energy, momentum, other properties often come in discrete packets, or quanta. Quantum gravity suggests space-time itself might be quantized. Time might not flow smoothly, but jump in tiny discrete steps. There might be a minimum possible duration, a fundamental tick of the cosmic clock, called the Planck time. It's incredibly small, about 1044 seconds. Below that scale, the very concept of time might just cease to make sense.
Like pixels on a screen. You can't zoom in forever.
That's a good analogy. Loop quantum gravity, one of the main approaches to this, predicts exactly that. Space-time is made of elementary grains or loops. Time progresses in discrete jumps as these structures interact and reconfigure. Like a kangaroo, not a smooth glide. There's also a minimum length scale, the Planck length, about 1033 centimeters.
And quantum mechanics also brings uncertainty, right? Like an electron being in multiple places at once.
Yes, indeterminacy and superposition. Quantum gravity suggests space-time itself isn't always sharply defined. It can exist in a fuzzy superposition of different shapes, different configurations. This fuzziness means the relationship between events can become uncertain. An event might be probabilistically both before and after another event until some interaction forces a more definite relationship. The clear distinction between past, present, and future gets smeared out at this fundamental level.
So things only become definite when they interact.
That's a core idea in quantum thinking applied here to time itself. The concreteness of a temporal relationship, or even duration, might only emerge in relation to a specific physical system interacting with the gravitational field, which is space-time. Without interaction, it's just a haze of possibilities.
Yeah.
So time isn't even a coherent canvas anymore. It dissolves into this network of relationships, only becoming somewhat definite locally through interaction. The crumbling is complete. So, yeah, after all that crumbling, no unity, no direction, no universal now, no independence, no continuity. What are we left with? It sounds like nothing, a void.
But physics isn't saying nothing happens, quite the opposite, right? It's saying change is everywhere. It's just not ordered by this single overarching time.
Exactly. This isn't a static picture. It's perhaps even more dynamic. But it forces a fundamental shift in how we think about reality. We need to stop thinking about the world as being made of things that endure through time and start thinking about it as being made of events or processes.
Okay, explain that difference. A thing versus an event.
Think about a kiss. A kiss is clearly an event, a process. It happens, it unfolds, it ends. It makes no sense to ask, where will that kiss be tomorrow? Right. Now think about a stone. We instinctively classify that as a thing, something solid, enduring, persistent.
Yeah, seems pretty thing-like to me.
But from the perspective of fundamental physics, that stone is also just a very long, very complex event. It's a temporary configuration of quantum fields, a pattern of vibrations holding itself together for a while. Over time, even the hardest stone erodes, changes, eventually disintegrates. Its apparent permanence is just a feature of our timescale. Fundamentally, it's a process, a happening, just like the kiss, only slower. The world is made of happenings, not of static objects.
So this implies a kind of historical mistake in Western thought, focusing too much on permanence, like Plato looking for eternal forms, or even Kepler trying to fit planets into perfect, unchanging geometric shapes.
You could argue that yes, they were looking for the unchanging shape of things. But the real breakthroughs in physics came when people like Galileo and Newton started focusing on the dynamics, how things change, how processes unfold. Quantum mechanics is all about dynamics, probabilities of transitions between states. The world seemed to be fundamentally about becoming, not being. And the absence of a fundamental time variable just underscores that. Change is primary, relationships are primary, processes are primary.
This also helps sort out those philosophical tangles, like presentism versus eternalism.
It really does. Presentism, the idea that only the present is real, fails because, as we saw, there's no objective universal present. Whose present are we talking about? And eternalism, the block universe idea that past, present, and future are all equally real, laid out like a frozen block, doesn't quite capture it either. Because change is real and fundamental in this picture. It's just not ordered globally. The world is dynamic and effervescent, not a static block.
So the confusion comes down to language. Our grammar forces us into these boxes.
Largely, yes. Our language has evolved based on our everyday experience, which does have a clear past, present, and future locally. So our grammar is built around that absolute distinction. It's like those ancient mapmakers struggling with up and down once they realized the earth was round. The words themselves aren't wrong, but their meaning becomes relative, context-dependent. We need a new intuition, maybe even new ways of speaking that reflect the relative relational nature of time.
That makes me think about that famous Einstein quote again about the distinction between past, present, and future being a stubbornly persistent illusion. It sounds like eternalism, like he's saying change isn't real.
Ah, but the context there is so important. It's often quoted in physics discussions, but he wrote it in a letter of condolence to the family of his lifelong friend Michel Besso, right after Besso died. Einstein himself was near death. He wasn't making a cold, hard statement about block universes. He was offering human comfort, saying in essence that from some larger perspective, the distinction between Besso being alive and Besso being gone might seem less absolute, less final. It's about the emotional weight of time and loss, more than just abstract physics.
That changes everything about how I hear that quote. It's profoundly human, not just physics jargon.
It really is. Physics tells us the universal present is an illusion, but our experience of flow and change, even if relative and emergent, is certainly real to us.
Okay, so if the world is events and processes, and there's no fundamental time variable to track them, how do physicists actually describe change? How do the equations work?
They work by describing relationships between variables. Instead of saying how variable x changes with time t, you describe how variable x changes with respect to variable y, or how variable z correlates with variable w. Think back to Aristotle. Time is the measure of change. We can measure how the position of a pendulum changes relative to the ticking of a clock's hands, or how temperature changes relative to pressure. You don't need an external absolute time, you just need the relationships between the physical quantities themselves.
So the laws relate variables directly to each other.
Exactly. The first attempt at a fundamental equation for quantum gravity, back in 1967 by Bryce DeWitt and John Wheeler, famously had no time variable in it at all, the Wheeler-DeWitt equation. It doesn't describe evolution in time. It's more like a master equation that describes the correlations between all possible configurations of the universe's geometry and matter fields. It tells you the relative probabilities of different states existing in relation to each other.
And loop quantum gravity, the modern theory you mentioned, builds on that.
It does. It uses those spin networks we talked about, the fundamental grains or loops of quantum space. Well, these networks don't exist in space. They are space. They're defined by their connections, their relationships of adjacency. And the way these networks change, transforming one into another, happens in discrete steps. The history of these transformations, these quantum leaps of geometry, is what physicists call spin foam.
Spin foam, like a foam made of space-time events.
Kind of. It represents the probabilities for different sequences of geometric transitions. It's fundamentally probabilistic, relational, and timeless description. It's this incredibly dynamic, fluctuating foam of quantum events appearing and vanishing, interacting. That's the bedrock reality physics points to, a world without our familiar sense of time.
Right, so we've reached the bottom, this spin foam world without time. Now, the big question, how do we get back? How does the smooth-flowing, directed time of our everyday experience emerge from that timeless quantum fuzz?
Emergence is the key word. Time as we know it isn't fundamental. It's an emergent phenomenon. Like the wetness of water emerges from the interactions of H2O molecules, even though a single molecule isn't wet. Or a traffic jam emerges from the collective behavior of cars, though no single car is the jam.
Okay, so time is like a macroscopic effect built on top of a timeless microworld. Where does the flow come from first? You linked it to ignorance and blurring before.
Yes, let's revisit thermal time. Remember Boltzmann and entropy. The idea was that entropy increases because we look at the world in a blurred way. We only track macroscopic variables, ignoring the micro details. Now, flip that logic. In a fundamental system with no special time variable, if you choose to describe it macroscopically, if you introduce blurring by averaging over many microstates, that very act of blurring defines a variable that behaves like time.
How does blurring define time? I'm still not quite grasping that connection.
Think of a complex system, like that gas in a box. At the micro level, maybe nothing is fundamentally changing in a directional way. But once you decide to only measure, say, the average energy in the left half versus the right half, a blurred view, you'll almost inevitably see the system evolve towards equilibrium where the energy is evenly spread. Why? Because there are vastly more microscopic ways for the energy to be evenly spread, high entropy, than for it all to be bunched up on one side, low entropy. Your blurred viewpoint automatically reveals the statistical tendency towards equilibrium. The flow towards equilibrium becomes your measure of time's passage.
So the statistical drift towards the most probable messy state, which only becomes apparent when I blur my vision, is what I perceive as time flowing.
That's the core idea of thermal time. The macroscopic state, determined by our coarse graining, by our ignorance, identifies a variable that flows because of the statistical properties of the underlying system. It's not time causing entropy to increase. It's the statistical tendency, revealed by blurring, that creates the phenomenon we label time.
So, my experience of duration, second by second, is literally a product of my own brain's inability to process the full quantum state of the universe.
Totally. Or maybe empowering. It means our reality is tailored to our way of interacting with it. It's not trivial, it's profound. This emergent time, born of ignorance, is deeply tied to thermodynamics and information processing.
And you mentioned quantum time as well, related to things not commuting.
Yes, quantum mechanics adds another layer. The fact that the order of quantum interactions matters, measuring position then momentum gives a different result than momentum then position, introduces a kind of primitive sequencing. Interaction A happening before interaction. B has physical consequences, even without a background clock. This non-commutativity provides a basic inherent directedness to quantum processes.
And these two ideas, thermal time from blurring and quantum time from non-commutativity, are they separate things?
The current understanding is that they are likely deeply intertwined. Two aspects of the same underlying phenomenon. Both stem from the relationships between parts of the system and the observer, and the inherent limits on information. So the conclusion remains. The familiar time of physics, the parameter t in many equations, seems to be an emergent property rooted in statistical mechanics and quantum interactions, ultimately reflecting our incomplete knowledge of the microworld. Time is ignorance.
Okay, that gives us the feeling of flow, of duration. But it still doesn't fully explain the direction, does it? Why does this statistical clock only run one way from what we call past to what we call future? It all hinges on that mystery. Why was the universe's entropy so incredibly low way back then?
That is the big cosmological mystery. Why did the universe start in such a special, highly ordered, improbable state? The conventional answer is we don't know. It just was. But there's a more speculative and perhaps more satisfying line of thought that ties it back to us, the observers.
Back to perspective again.
Back to perspective. Remember, entropy itself is relative. It depends on which variables you choose to track on your blurring. What looks ordered, according to one way of blurring, might look disordered according to another.
Right, so maybe the low entropy of the early universe isn't an absolute fact about the universe's initial state.
Exactly. This is the extravagant supposition, as Carlo Rovelli calls it. Maybe the apparent low initial entropy isn't a statement about the total state of the very early universe, but rather a statement about the specific way we, as physical systems, happen to interact with it. Perhaps we interact with the universe only through a specific subset of its variables, and relative to that subset, the early state looks incredibly ordered.
Like the spinning sky. We thought the whole cosmos spun around us until we realized we were the ones spinning, creating that perspective.
That's the analogy. Could the arrow of time be a similar perspective effect? Maybe the universe as a whole doesn't have a preferred direction, but we, because of the specific way our biological systems process information and interact with our environment, are coupled to the universe in such a way that we perceive a strong entropy gradient.
So we're special systems.
In a way. The universe is vast, with countless configurations and subsystems. It seems plausible that within this vastness, certain types of systems naturally arise, systems like us, whose internal workings and interactions happen to align with a particular definition of macroscopic variables that makes the past look ordered and the future disordered. For these systems, the second law holds true. Entropy increases, irreversible processes happen, memories form, and time appears to flow relentlessly forward. For other hypothetical systems interacting differently, maybe time would seem to stand still or even run backward relative to us.
Wow, so the arrow of time might be real for us because of how we're built and how we connect to the cosmos, even if it's not a fundamental property of the whole universe.
That's the idea. And this increasing entropy, this flow from order to disorder dictated by our perspective, is what actually drives everything we see happening. We often think the world runs on energy.
Yeah, energy makes things go.
But energy is conserved. The total amount doesn't really change. What gets used up, what gets consumed is low entropy. Order. That's the precious resource. Think about the sun. It doesn't just give us energy, it gives us ordered energy. High energy photons come in, low entropy, get used by plants and eventually us, and then radiate away as lots of low energy infrared photons. High entropy. Life runs on consuming the sun's low entropy.
So it's not an energy crisis we should worry about, it's an entropy crisis. We're consuming order.
That's a great way to put it. The entire universe, from stars forming to life evolving, is driven by processes that increase overall entropy, consuming pockets of low entropy along the way. And it's not always a smooth process. Things get stuck in temporarily stable, low-entropy states. Think of a pile of wood, stored chemical order, or a cloud of hydrogen gas, gravitational potential order. They sit there until something triggers a process, a spark, or gravitational collapse that allows entropy to increase rapidly.
Like life itself. Is life just a way to burn through low entropy faster?
In a sense, yes. Life creates local pockets of order, our bodies, our societies, but it does so by accelerating the consumption of low entropy from its surroundings, food, sunlight, and dumping high entropy, heat, waste, back into the environment. We are incredibly effective entropy-producing machines. Even something as simple as a stone falling and coming to rest isn't fundamentally about reaching the lowest energy state. It's about converting its ordered mechanical energy into disordered heat energy in the ground, increasing the total entropy. The second law is pulling the strings everywhere. That halting, irreversible cascade towards higher entropy is the physical manifestation of the flow of time that emerges for us. #tag outro.
Okay, let's try and piece this back together. We started with time feeling absolute, universal, directional. Then physics chipped away at it. Time lost its unity. It runs differently everywhere. It lost its fundamental direction. The basic laws are reversible. Direction comes from heat and statistics. It lost the universal present now, is local. It lost its independence as part of the dynamic gravitational field. And finally, it lost its continuity. It's likely granular, fuzzy, and relational at the quantum level.
Yeah, a complete demolition job, really.
Mm.
What's left at the bottom is this weird, timeless, probabilistic network of quantum events, spin foam. But then, crucially, our familiar sense of time emerges back out of that. It emerges primarily because of our blurred perspective. We don't see the micro details, so we perceive the statistical drift towards disorder, entropy. And the specific direction of that drift, the arrow of time, might be a consequence of our particular perspective, the specific way systems like us haven't interacted with the universe, making the past seem exceptionally ordered to us.
So, the great mystery of time. It turns out to be less about the cosmos itself, and maybe more about us. Our limitations, our perspective, how we process information. Our whole sense of being creatures in time seems tied to this fundamental ignorance.
It really seems that way. Our ability to remember, to anticipate, to feel the passage of moments, it all seems deeply connected to thermodynamics, to entropy, and to the specific coarse-grained way we experience reality.
Which leaves us with a pretty wild final thought. If time, with all the baggage it carries, anxiety about the future, regret about the past, that feeling of being relentlessly swept along, if all that is born from our limited, blurred perspective, what would happen if we could overcome that?
What if, hypothetically, we could perceive the world without the blur? Like that character, Charlotte, in the thought experiment who gains access to total information.
Yeah, if we saw the whole probabilistic, timeless reality directly, would the feeling of time vanish? And if it did, would the mental confusion, anguish, fear, and alienation that the river of time imposes also disappear? Could seeing eternity clearly make it not so scary?
That's definitely something to ponder. What would reality feel like without the filter of emergent time? Something for you to think about.